Thanks for joining me. My name is Marco Franceschetti, and in this video I will present you a work which has been conducted recently with my supervisor, Professor Johann Eder, and my colleague Josef Lubas at the University of Klagenfurt in Austria. The title of our work is Scheduling Processes Without Sudden Termination.
Imagine you are giving a presentation on the importance of time management in business processes. You're an expert in the field, and as long as you know how much time you have for your presentation, you're able to cater any kind of presentation, be it a 1-minute elevator pitch to a full 2 hours lecture. For today, they told you you have between 10 to 20 minutes. Okay, that's business as usual, no big deal. You start. And now let's suppose we are 12 minutes in, maybe someone is still listening to you, and then the session chair comes to you and tells you, you need to be done in 1 minute. What? I'm not done yet. I have still so many great results to show, and now I will not be able to tell them. That's quite an unpleasant situation, right? So, to my luck today, this is a pre-recorded video presentation, so nobody will interrupt me. I promise you I will stick to the time window which is given for this presentation. In the following, I will tell you how we reach a formalization for this problem in the context of business processes, and then I will also show you how we manage to reach a solution to the problem.
So let's consider an example which is based on a process model. Here you can see a procurement process which starts with an activity process order. Process order can take between 1 and 2 time units, and this duration is under the control of the executor, who can decide for how long this activity should last, as long as it is within the specified range. We call this type of duration non-contingent. Then we have two activities which are executed in parallel. Range shipment is still under the control of the executor, who can decide for how long to carry on this activity, be it 5, 6, or 7 time units. Approved payment is contingent, which means it's not under the control of the executor, and it's only observed at runtime to take 2, 3, 4, up to 5 time units. Finally, deliver goods is executed, and this is also non-contingent and will take 2 to 7 time units. Here we see also two red arrows. These represent temporal constraints between the parallel activities. In particular, they impose that approved payment starts at most 1 time unit after the start of a range shipment, and that a range shipment ends at most 1 time unit after the observed time of end of approved payment. Now, to meet the duration constraints and these explicit constraints, we observe that we will need to start a range shipment without knowing in that moment when it will have to end. Later, this activity will have to be suddenly terminated after observing the end of approved payment. So what we would like to have here is to know at the start time of the activity for arranging the shipment when we are expected to terminate it, so that we don't have to suddenly stop its execution. Now let's make a step back and discuss which are the elements we need to consider for our problem. Typically, when we talk about the temporal aspects of business processes, we refer to process deadlines, minimum and maximum task durations, and temporal constraints, where by temporal constraints here we mean upper bound constraints and lower bound constraints, where an upper bound constraint refers to stating a maximum allowed distance between two events in time, and a lower bound constraint is imposing a minimum distance in time between two events. Altogether, these elements concur to what we consider as the temporal correctness of a process, which is basically the capability of executing a process while meeting all these temporal requirements. So far it seems it's the very same old story, right? Well, what is grinding the gears here is contingencies. What do I mean by that? Well, in fact, we need to distinguish between two types of durations, contingent and non-contingent. Contingent durations are those which cannot be controlled by the executor, but only be observed at runtime to take some time between a specified minimum and maximum, whereas a non-contingent duration can be controlled by the executor in taking some time between, again, a specified minimum and maximum. I give you an example for contingent duration. Now, the most typical one is that of a bank transfer within the European Union. Suppose we are sending some money from Madrid to Berlin. Now, the banking system in Europe is telling us that they need between 1 and 4 days for completing the transfer. And we, as clients, have no way to enforce an actual duration within this time window. We will only be able to observe when the transfer is actually completed by the system. Given that, it is now clear that we need a refined notion for the temporal correctness of the process. In fact, now we need to ask ourselves this question. Are we able to steer the execution of the process by assigning timestamps for the starting and finishing of activities in a reactive manner in response to those observed durations of contingent activities? Now, to cite someone who is more famous than me, if the answer is yes, we can, then we say that the process is dynamically controllable, and therefore we have dynamic controllability as the notion for temporal correctness of a process model. And how do we check whether a process is dynamically controllable? Well, actually, there is already a number of techniques available out there. One of the most established ones, which we are also considering here in this work, is based on mapping process models into simple temporal networks with uncertainty, or STNUs for short. Basically, an STNU, like the one depicted here, is a graph-based formalism in which we have nodes and edges. Nodes are representing time points, and edges represent constraints between time points. We have two types of edges, contingent and non-contingent ones, which are basically representing the two types of durations, which I have discussed already in the previous slide. Over time, a number of algorithms which are sound and complete have been developed for checking the dynamic controllability of an STNU. These are typically based on propagating the existing constraints, so deriving new edges such as the red one in the image here. And we can take those techniques and say that a process model is dynamically controllable if its equivalent STNU is dynamically controllable. So a dynamically controllable process basically requires a dynamic schedule. On the flip side of the coin, however, dynamic schedules may require that certain activities have to start without knowing when they must complete, with the consequence that certain activities will have to suddenly terminate. Now, while for some activities this poses no problem, think for example of waiting tasks. For other non-contingent activities, a sudden termination may be highly undesirable or unacceptable or even impossible. In particular, think of activities involving human actors or activities which are invoking uninterruptible external services. So that's when we realized we needed to define a new type of activity duration, semi-contingent. So now we distinguish between non-contingent, semi-contingent, and contingent activities. The duration of contingent activities, we already know, by their nature cannot be controlled. Thus, it cannot be known when they will actually terminate. The process controller may, however, control the duration of non-contingent activities at any time. This means in particular that they are allowed to start with no knowledge about the time when they have to end. Thus, we concede to be suddenly terminated for non-contingent activities. With semi-contingent activities, in contrast, we are required to know at their start time when they must terminate. This means that the process controller can set the duration until the activity starts. And as a direct consequence came our second contribution of this work, which is the formalization of a new type of controllability, which we called semi-dynamic. So now the question is, can we steer the execution of a process, assigning the timestamps for starting and finishing the activities in a reactive manner in response to the observed durations of contingent activities, such for dynamic controllability? But now we add the following: with the end times of the semi-contingent activities known at their start time. And if the answer to this question is yes, then we say that our process is semi-dynamic controllable, and therefore we have this new notion for temporal correctness in the case of processes with semi-contingent activities.
Our research was driven by two questions. The first question was, how can we verify whether in a process model there are certain activities which are subject to a potential sudden termination? The second question then was, can we do something about that? Can we modify our process model in some way such that we are sure that these activities will not be suddenly terminated? Well, actually, we found out that there is a number of patterns or constellations of activities and constraints between them, such in the example here, which lead to actually the sudden termination of a semi-contingent activity. What we have also found out is that for these constellations, we have corresponding constraints which we can calculate and add to the process model, like we have done here, such that fulfilling those new temporal constraints will avoid for sure that the semi-contingent activity will have to be suddenly terminated.
In particular, we identified 6 constellations or patterns which lead to a sudden termination of a semi-contingent activity. In the first column of the table, we report constraints which need to hold between a contingent and a semi-contingent activity for each of the constellations. In addition to that, also certain conditions on the bounds of the temporal constraints and on the durations of the two activities need to hold to have a potential sudden termination. In the second column of the table, we report the negation of that condition. Why? Because if we negate that condition, then we are sure that sudden termination is avoided. Therefore, from this negation, what we see in the third column of the table is the temporal constraints which correspond to that negation. And these are the temporal constraints which we can add to our process model in order to avoid the sudden termination of a semi-contingent activity depending on its pattern. For details on each of these patterns, I refer to the paper. After introducing new temporal constraints into a dynamically controllable process model, we need to verify whether the process model remains dynamically controllable. Here we see an example of a process model in which the constellation of the semi-contingent activity arrange shipment, the contingent activity approve payment, together with the upper bound constraints, which are depicted in black here, lead to the sudden termination of a range shipment. We were able to calculate that in this case, sudden termination can be avoided by adding two new temporal constraints, an upper bound and a lower bound depicted in red here, which basically force a range shipment to terminate exactly 4 time units after approved payment started. We can verify that even with the addition of these new temporal constraints, it is still possible to find a dynamic schedule for the process model, which meets all the temporal constraints. So in this case, the process model remains dynamically controllable. What happens in this other case instead? So here we have a different constellation of temporal constraints, which are still depicted in black between our activities range shipment and approved payment. The associated constraints for avoiding sudden termination now are an upper bound constraint with bound 7 and the lower bound constraint with bound 8. These are still between the start time of approved payment and the end time of arranged shipment. Now in this case, we cannot find a schedule for starting and ending the activities which meets all the temporal constraints. This means that if we want to avoid sudden termination of arranged shipment in this process model, we need to give up on meeting some temporal constraints. So in this case, we conclude that the process model is not semi-dynamic controllable. So our last contribution is a procedure to check whether a process model is semi-dynamic controllable. The idea is very simple. First, we map our process model into a temporally equivalent STNU. Then we iterate over all the existing sudden termination constellations. For each such constellation, we add corresponding STN edges in the STNU for the constraints which we need to add to avoid sudden termination. And we check if the STNU remains dynamically controllable. If at the end of the iteration the STNU remains dynamically controllable, then we are avoiding all sudden terminations and the STNU is dynamically controllable. Therefore, we have a semi-dynamic controllable process model. So, to conclude, with this work, we have shown that activities which have uncontrollable durations require the existence of a dynamic schedule in order to meet all the temporal constraints in a process model. However, these dynamic schedules may lead to suddenly terminate certain activities. That means they start without knowing when they must finish. We have identified a number of constellations of activities and constraints between them which lead to their sudden termination. We have introduced the notion of semi-dynamic controllability as the notion of temporal correctness for addressing such situations. Finally, we have presented a verification procedure for semi-dynamic controllability, which is based on the identification of patterns and is based on STNU dynamic controllability checking techniques. So this is it from my side. I would like to thank you very much for your attention.